Now we'll be practicing a little bit more with these exponential equations. So we already did example number 5, parts A and B in the last video. And remember, there are two basic types of exponential equations as we're kind of looking at it. One is an exponential equation like numbers 1 through 4, where we can write as the same base on each side. So for example, in number 3, we wrote these both in base 2 terms on either side and then set the exponents equal to each other. The second type of exponential equation is when that's not possible, then our new technique is we just take the natural log of both sides. So that's what we did in number 5. Because we had base e on one side, we couldn't write base e on the other side because it's an irrational base, and we need a calculator to do that. Okay, so we're using that natural log approach in these next few examples. So for number 6, it says find the time. I just want to make a note that that's what we're looking for, time. Find the time it takes $2,000 to triple. So 3 times the original. So find the time it takes $2,000 to triple at 6% compounded continuously. And by the way, if $2,000 triples, then it's going to become $6,000, right? 2,000 times 3 equals 6,000. All right, and we're given this formula because it's compounded continuously. We're going to use this, I call it the PERT formula. So A equals P times E raised to the power RT. So remember, A is the accumulated amount. So switching colors. That's going to be the 6,000. That's what the 2,000 turns into. It accumulates to 6,000. So I'm going to write 6,000 on the left side equals P is our initial principal, so our initial investment. So that's going to be our 2,000. So initially we put in $2,000 and then it tripled, right, into 6,000. E is our base, so I'll write down that E. And then raised to the power R times T. We know our interest rate is 6%, so R is going to equal 0.06 as a decimal, so 0.06, and then T is the unknown. Remember that we're looking for the time it takes, so T is our unknown. So that's the equation we're trying to solve. Now notice that we have that base E, so it's not going to be possible to write a base E on the left-hand side to match it, because E is a weirdo. So we're going to use this tactic. So the take the natural log approach. So remember, first we want to fully isolate that exponential, in this case on the right side of the equation. And then we're going to take the natural log of both sides, apply the power rule, and solve. So first, that isolate step means I'm going to divide out that 2,000 from both sides. And this gives me 3 equals e to the power 0.06t. And 3, we knew that this was tripling, so that's not a huge surprise. All right, so now that we've got that base e isolated, now I'm going to take the natural log of both sides. So natural log, natural log. So this gives me the natural log of 3 equals, and then on the right side, the natural log of e to the power 0.06t. I'm going to apply the power rule, pull that power forward, so 0.06t times the natural log of e. And remember, the reason this is helpful is the natural log of e is just equal to 1. So now we have natural log of 3 equals 0.06 times t. And now we just need to divide both sides by 0.06. All right, so let's put that in our calculator using the ln key on the left-hand side. So natural log of 3, then I'll use that right arrow in the top right corner to scoot out of the parentheses, and divided by 0.06. And it depends on our rounding instructions, but let's say they want us to round to the nearest tenth. Something like that. All right, so time is approximately 18.3 years. Remember that that PERT formula always gives us years. Time is in years, so our result will still be in years. Okay, for number 7, determine the interest rate. So now that's what we're solving for in this problem. Interest rate R, so that's what we're looking for, required for an initial investment of $5,000, so that's going to be our principal P, to accumulate to $7,500, so that's going to be our capital A, our accumulated amount, in 5 years, so time is 5 years, if the interest is compounded continuously. So because it's compounded continuously, again, we're going to use this PERT formula. So A equals P times E raised to the power RT. Okay, so let's fill in what we know. Accumulated A, 7,500, equals our principal P, 5,000, times E raised to the power R, which is unknown, times T, which is 5, or we can call that E to the power 5R, of course. So following our steps, first we're going to isolate. Okay, and if you're not sure, 7,500 divided by 5,000 gives you 1.5. So I'm going to rewrite this as 1.5 equals our base E raised to the power R times 5. I'm just going to make it a little prettier and write it as 5 times R. Now that that base E is isolated, I'm going to take the natural log of both sides. So this gives me natural log of 1.5 on the left equals, and then we apply the power rule on the right-hand side, 5R times the natural log of E. And remember that natural log of E is equal to 1. So now we just have natural log of 1.5 equals 5 times R. Divide both sides by 5. So we have that our interest rate R equals natural log of 1.5 divided by 5. So let's crank that out in our calculator using the ln key. Natural log of 1.5, scoot out, divided by 5. And let's say we want to round to the nearest tenth of a percent. So 0.081 is 8.1%. Moving that decimal place 2 to the right. So the nearest tenth of a percent there. Okay, so that wraps up our exponential equations. And just to prep us for the next video, oops, sorry, I lied. There are more exponential equations, and then we'll prep for the next video. So let's take a look at number 8. The instructions here say solve by taking either the natural logarithm or the base 10 logarithm, common log, of both sides. Express your answer in both exact form, and then approximate this to the nearest thousandth if necessary. All right, so notice in the instructions they say take the natural log or the common log. Both methods work. I just like to take the natural log because that base E comes up quite often, so I usually just stick with the natural log, but if you want to play around with common log, you can as well. So I'm going to stick with taking the natural log of both sides. All right, so in part A, we've got a base 4. On the right-hand side, if we could write 345 with a base 4, that'd be super, but we can't. So instead, we're going to take the natural log of both sides. I can't isolate that exponential term on the left-hand side, so I'll go ahead and take the natural log. So just writing this a little bit bigger, 4 to the power 2x equals 345. I'm going to take the natural log of both sides. And remember, this allows us to apply the power rule. So this gives me 2x times the natural log of 4 equals the natural log of 345. All right, now in previous examples, after we applied the power rule, we would have the natural log of E, like we did right here, for example. Oops, can't write there for some reason. Where is it? Here. there we go, natural log of e, which we would convert into its equivalent 1. But down here we have natural log of 4, which is just something funky, right? Natural log of 4 is that lovely number. So we're not going to simplify it because we can't simplify it to a nice pretty integer. So instead, we're just going to focus on isolating x. So to isolate x, everything currently is being multiplied by x on the left side. So I'm going to divide by that 2, and I'm going to divide by the natural log of 4. And I'll match it on the right-hand side to natural log of 4. You can write that multiplication symbol, but you don't need it, doesn't matter. So these cancel out on the left, and these guys cancel out on the left. So our exact answer, x equals the natural log of 345 divided by 2 times the natural log of 4. And then cranking that out in our calculator to get the approximate answer rounded to the nearest thousandth. Approximate. Clear this out. So again, we're using that natural log key on the left-hand side. Natural log of 345, and then I'm going to scoot to the right, divided by, and I just want to make sure that that 2 times natural log of 4 all stays in the denominator, so I'll use my parentheses keys above the 8 and the 9. When in doubt, use your parentheses. 2 times the natural log of 4. Scoot out of there and put my parentheses and hit enter. So it's approximately equal to 2.108, rounding to 3 decimal places. Okay, and before we move on to part B, I just want to point out that for our exact answer, we got natural log of 345 divided by 2 times the natural log of 14. In the denominator, if I apply the power rule in reverse, 2 times the natural log of, sorry, I said 14, I meant 4. 2 times the natural log of 4 is actually equal to 2 times, times the natural, let me start over, let me rewind. 2 times the natural log of 4 is equal to the natural log of 4 squared, which is the natural log of 16. So if I type in my calculator, natural log of 345 divided by natural log of 16, I still get the same approximation. So you might run into a case where you have a different exact answer than I do, but when you type it into your calculator, if you type it properly and you're getting the same approximate answer, then we should have the same equivalent exact answers. So I just want to point that out. There are different ways to write these exact answers. Sorry, a little over-caffeinated today. Okay, looking at part B, 5 to the power x minus 3, I'm just going to write it to make it look bigger, equals 137. I can't write 137 with the base of 5, or at least I don't know how to. So we're going to use this natural log approach. So take the natural log of the left and the right side. And then that allows us to use the power rule. So x minus 3 equals, x minus 3 times, as I was saying, the natural log of 5 equals the natural log of 137. And now we're trying to solve for x. And again, there are different routes you could take. Some of you guys might be distributing at that point, and that's totally fine on the left-hand side. I'm going to go ahead and divide the natural log of 5 from both sides. So this gives me x minus 3 equals natural log 137 over natural log of 5. And then at this point, I can add 3 to both sides. So this gives me x equals natural log of 137 divided by natural log of 5, and then plus 3 for my exact answer. And approximate, let's go ahead and type this into our calculator. Natural log of 137, scoot out, divided by natural log of 5. So that's 3.057-ish, and then when we add 3, I just hit the plus sign, and it's going to pull down my previous answer to give me 6.057. Rounding to the nearest thousandth.